This can also be formulated equivalently as a max problem. So min or max, a linear function subject to linear inequalities and equalities, is a linear program. The geometry of linear program is inspiring. Unlike more general convex problems, the optimal is always obtained at the edge. Right, so this is, for example, for this problem here, where we're trying to minimize x plus y, and we find that it is exactly at this edge here. So the techniques for solving linear problems have been very efficiently developed, and we can, this is the class of problems for which we can have the largest problem size and still efficiently solve them. Now, as I mentioned before the break, the specific nature of an optimization problem is not something intrinsic in the natural problem that we have. It is something that is depending on the formulation we give. So some problems may appear as linear problems after some transformation. So one of the things you will have to learn during this module is to immediately recognize the things that can be transformed into linear problems, even though they are not at the beginning. Here are two problems that are obviously not formulated as linear programs or linear problems. Which, if any, of the two can be, after transformation, transformed into an equivalent problem that will be a linear problem, linear optimization problem. I close in 5 seconds. B is easily transformable into a linear problem, A not. This is correct. At least today we haven't found a way to transform exactly a square into a linear program, and this can probably be proven, but at least it's easy to see we can't find easily a solution. More interesting is to learn the technique to transform the other one. So the other one was minimize a max of linear functions. Then max and minimize a max, can easily be transformed into adding dummy variable t. So there is a price to make it linear. We have more variables, so we will increase the complexity of the problem. And then minimizing the max of those two quantities is the same as minimizing t over the constraint that t is larger than or equal to those two quantities. And the key observation is that saying that a number t is larger than a first expression and a second one is equivalent to saying that it is larger than the max of the two. And now if we minimize some t, which is an independent variable, there is no other constraint on t than those two that we have introduced. So finding the t that is as small as possible and is larger than that, then the answer is it is the max. So the smallest t is the max. Right? So this problem is the same as minimizing this max over this constraint. So we can eliminate t from this problem. So in other words, if I give you this problem and I ask you, can you transform this problem into an optimization problem that has fewer variables, can you eliminate t? The answer is yes, I can eliminate t, and I will find my original problem, which is this one. But the interest is in the converse direction. And this is a generic transformation that we will frequently use in all the formulations of energy systems in general. If I have to minimize t over, no, that's exactly the proof that we have done before. So minimizing, so the trick we gave that minimizing t over a constraint of this thing is the same as minimizing f0 of x and y. Right? Which means that in general, any problem of the form an objective function which is given by the max of a set collection of functions is the same as minimizing t, where t is larger than each of the functions here. So that's an important transformation that is routinely used in all formulations of optimization problems that we use in grids, but in energy systems in general. We can even go one step further. If we are embarrassed by nonlinearity, for example, of the square function, this x square function cannot be expressed as a maximum of linear function, at least not exactly, but approximately it can. Depending on the accuracy I want to have, I can say that here I'm illustrating this with those four functions, L1, L2, L3, L4, then x square can be approximated by the max of those four functions. So I take the max of those four straight lines. Of course, for a very large value of x, I will have something that is not linear. I have a poor approximation. But on this interval that is shown on the figure, I have a decent approximation of the square function. That's a trick that is sometimes used to transform your problem into a linear one if you have to. Here I'm proposing a problem, P, which is nonlinear. Two reformulations. Is any of those a correct reformulation of P as a linear program? It's getting better. Okay, I can now close the poll. Okay. The correct answer is A. This is because the absolute value of something is the max of this thing and the opposite. Absolute value of y is the max of y and minus y. That's not the usual way we think about it. We think the absolute value, you take the number and you remove the minus sign. That's the intuitive way, at least I have. But constructive way that can be used in our setting is to say the absolute value of something is the largest of this thing and minus this thing. If this thing is negative, the minus this thing will be positive, and the larger will be the minus. If it's positive, the larger is without the minus in front. And if x and y are variables, we have no clue which one is positive, which one is negative, but this is certain. Which means that this problem is the same as minimizing a max of linear functions. Therefore, it's the mean of t over those two quantities here. That's a quite useful trick that we will use a lot, that is used in general a lot, when we have to take costs, for example, that are a penalty function. For example, we want to run a grid with certain constraint on some values, but it's a soft constraint. We would like something to be not too large. One way to do it, which is very frequently used, is to take a penalty function, which is a square of the deviation that you have. But if you take the square, you will have something nonlinear. If you take the absolute value instead of the square, you will have something linear, which will greatly simplify your problem. So if you have the choice of the problem formulation, very often that's the case. Our problem as energy or smart grid specialists is to model a physical reality and find an operational solution to a problem. So the formulation of the problem is often part of our job, more than the solution, in fact. But we have to know which kinds of problems are easy to solve. And the best and easier problem are the linear programs. So if you can make your problem linear, do make it linear. And one trick is to replace squares by absolute values, for example. So back to the AC-OPF problem. Here I'm writing something that says the AC-OPF problem is non-convex. And here is an illustration to show why. This is a minuscule grid with one slack bus and generator, which is bus 1, and bus 2 has simply a load. And I have some specific values of the line and the admittance of the line. And I'm looking at all the possible values of the power injections, PQ, or consumption here, minus injection, PQ, that satisfy the voltage magnitude constraints. Right, so what are all the PQ values? And the answer is given here. So P is on the x-axis, and Q on the, on the y-axis, and Q on the x-axis. And the feasible values are the red part here. So we see that this set is non-convex. Right? So this is all the feasible PQs for this line. If I'm interested in, if I assume the line current is not a problem, but line voltage might be a problem, which is often the case in distribution network. Then those are all the feasible P and Q. Now, if you want to optimize something, then depending on what you want to optimize, for example, if I optimize a linear function, and the curve optimize a function that is here, for example, I will find that there would be perhaps an optimal at this edge, but there might be also an optimal at another point. So we are in the typical non-convex case here. Perhaps you could criticize this line. What I wrote is not true, in fact. What could you criticize here? Well, what I should say more precisely is the formulation I gave before of the AC OPF problem is non-convex. I gave a rectangular coordinate formulation. Now, as I said before, the convexity or non-convexity is not a property that is kept under nonlinear transformation. So it's not a fundamental property of a problem. It's a property of a given formulation, of a given parameterization of the problem. So the more exact thing is, today, nobody has found a correct way of making this problem convex. So we can change into polar coordinates for PQ, for example, and it would, in this case, not really change the problem. As I mentioned, there are attempts, but the jury is still out to see what can be done with more recent techniques. What we will see are the classical techniques for making the problem convex. To make a non-convex problem convex, or in general to make a difficult problem less difficult, there are always two competing hacks, two competing ways of getting rid of the problem. The first way is to find an approximate solution to the exact problem. This is what I did in the previous slides when I asked F-min-con. F-min-con finds a solution which is perhaps the good one, perhaps is only approximate one. And this will work if the problem here is small. Another approach is to transform your problem into another one, which you hope is close to the original one and will be more tractable. Those are, we will see those two solutions now. So the first thing we see is of the second category. It's a radical transformation of the problem. It's very radical. It's often used, but we will, as we will see, it is so radical that, of course, it's not really credible, but it's used routinely for high voltage networks. It's called the DC approximation. It is based on the following assumptions that are true in high voltage transmission network. For example, Swiss Grid runs this to do their dispatch and verification and optimization every day. But of course, they don't just do it because it's grossly approximate. They still do some verification after that. This is probably not usable in distribution networks for the reasons we will see. So the main observation is that it applies in grids where the resistance is much less than the imaginary part of the impedance of the line. So So the reactance is assumed to be much larger than the resistance. And this is true at very high voltage, probably much less true at low voltage. It also works when the regime in which we operate the grid is the nominal one. So the grid, you can operate a grid in a very degraded regime. For example, if you're trying to to power a load that is 2,000 kilometers away from a generator, perhaps in southern Argentina you could do that, or in Chile you can put a generator on Terre de Feu, which is very, very far away, and you have an extremely long line, and you lose, the line losses are 2/3 of the generator power. You could have things like this in very special cases, but transmission grids normally do not operate in this mode, which means in particular that the voltages, the complex voltages, are very close to the nominal value of 1, which translates into 2. The module is close to 1, the voltage magnitude here, and the voltage angle, the argument of the complex voltage, is close to 0, relative to some reference, which is, for example, one of the generators here. So if we have those assumptions, then we can derive an approximation that's very easy to write. So I'm doing it here. I'm taking the accurate model of a line, which is called the pi model. So a line between bus K and bus L can be modeled, as you have seen in the previous module, by an impedance, longitudinal impedance, but also transversal impedances or admittances, so which are the typically purely reactive parts between the phases and the ground here. In the previous examples, I ignored them to simplify the notation. If we do not ignore them, in the previous equations, I had only this term for expressing the power flow on the line KL, but there is an additional term here which translates in the admittance matrix by the fact that the diagonal term of the admittance matrix have an additional component due to those are called the shunt elements. So those are the exact values. So Y is the longitudinal admittance, V are the complex voltages, and B are the transversal admittances, which are purely complex, imaginary. So if we do all the math of this, when we're interested only in the active power flow, we take the real part of this, and this is what we would like to approximate with a DC approximation. So first we say the resistances are small, so the G part of the admittance here, which is of the kind R divided by R square plus X square, is negligible. So we put it to 0. Right? And I'll say that the voltage magnitude is 1, and the voltages angles are small, which means we will replace exponential j theta for an angle theta by 1 plus j theta, which is the first order approximation of the exponential function. So let's do all this in this formula. So in this formula we will have the module, which is 1, and an angle, which will be a linear function of the angle. And this will give, this is what I wrote here, and by applying the approximation that I mentioned ago, we find the real part of that stuff here, which is a linear function of the angles theta. And we find that the power flow on the line KL is approximately equal to BKL. Well, what is BKL? Well, BKL is minus the imaginary part of the nodal admittance matrix of the longitudinal element, which is also the non-diagonal term of the admittance matrix, which is typically negative. So BKL is minus this, which is positive, times, so I call this capital BKL to have positive quantities here, times the angle difference. So that is the DC approximation. The DC approximation says you take the imaginary part of the admittance and of the lines, and this is the linear factor that multiplies the angle difference on the line. It's only approximate, and as I said, it's approximate only in high voltage networks, but it's a very useful physical approximation of how grids operate, how AC grids operates. And it tells us, in particular, the importance of the phase angles. So the phase angles are determining the power flows. And also it tells us that the power flows on a line cannot be controlled by simply routing power like I would do on a road network or on a communication network where a router can decide how many packets it sends on one line or the other. Here, the flow on the line is dictated by the angle difference. So it derives from a potential. I put potentials, which are the angles, on different nodes, and then the flows derive from that. So if I want a lot of flow to this point, I have to put a smaller angle here than there, and then the power will flow according to theta that we can interpret as a potential, or we can think it's similar. Those are the same equations we would have for water. If this is the altitude, and if the altitude of K is at a higher level than L, then there will be water flow from this point to this, roughly proportional to the difference in altitude of the reservoir. So that's the DC approximation. The good news is, of course, it is linear in theta, not in rectangular coordinate, but linear in theta here. Now, if we sum overall the branches, we obtain the power nodal injection, the active power nodal injections, which is equal to the sum of this. And if we take the sum of all the powers, which by the fundamental law of the physics of circuits is zero, there is power conservation at every bus, we obtain that the sum of the, so those are algebraic powers, it's positive or negative, the sum of all the injected active powers in all nodes with the DC approximation is zero. Now this sum, if we have the real value of the active power, not the approximated value, this sum is equal to what? It's the losses. It's the active power loss. The sum of all the algebraic power is the losses. So here 0 means the DC approximation ignores the power losses. So it can be used only for setting the direction of the power flows, but you cannot use it to estimate the power losses. So what is typically done by transmission grid operators, they plan their operation doing the DC approximation for testing which way the power flows will go. And then once they have obtained set points of the generators, they redo an exact load flow to compute the power losses, and then they charge it to the different participants in the market. So let's take this example again, and let's redo this approximation. Then we find here the power balance at node 1. So here we find the B term of the load between 1 and 2, of the line between 1 and 2. So this term is the power flow on the line 1, 2. This is the power flow on the line 1, 3. And we see that the power flow on the line 3, 1, so from 3 to 1, is exactly the opposite of the other one, which is the same as saying we ignore the power losses. So we have three equalities here. Of course, the sum of the three powers is 0, which means, in fact, out of those three equalities, one is redundant. So in fact, we have only two relations here. And to simplify, to further continue in the optimization problem, we can solve for theta in the set of equations. So if I assume I give you the active power injections P1, P2, P3, I can solve for theta. Now I have three angles and apparently three equations, but in reality only two, because the sum of the three equations gives 0 equals 0. So I have only two equations for three angles, but in reality I also have only two angles, because the angles are set to 0, for example, at the slack bus. As usual, the phase angles are not defined in absolute terms, but relative to one reference value. So I can invert this for theta 1, theta 2, and theta 3. And from this, I can, so the first step is to say the power flow on line 1, 2 is given by this. And I can use that to express the constraints on the, if I have here the branch flows, of course, in this, on this formulation, I cannot compute the line currents. In fact, the line currents are ignored of this formulation. If I had the line currents, I could compute the losses. Since I cannot compute the losses, it means I don't have the line currents. This is one of the justifications why people often use the maximum power flow on lines instead of maximum current. But here I can compute the maximum flow of lines using those, so I can express the quantities on the maximum flows of lines. Of course, I cannot express the voltage constraints because I'm assuming all the voltages are equal to 1 magnitude here. So the only constraints I can express with the DC formulation of the optimal power flow, called DC OPF, is the constraints on the power flows on the branches. So if I do that, I have a problem that has this formulation. The control variables I want to set are the power injections, active power injections, and here are all the constraints that I have written before, with constraints on the power injections and power constraints on the branch power flows. I did it for this problem, and this gives a very simple formulation where here the active power flows were G1, G2, G3. The flows on line 1, 2 is given by this simple formulation. Theta 1 is equal to 0. So I have 3 constraints in absolute value. The absolute value of Pij is less than this, which is, as we have seen, can be transformed into linear constraints. So this is exactly a linear program. Good program, therefore. I can easily solve it. I did it here. And this is the solution I find. I found now round numbers. I found only the active power flows. I cannot compute the reactive power flows with this formulation. And I found a solution that's significantly different from before, from the cost viewpoint, but not significantly different from the line viewpoint, from the power flows. So we find, like before, that this generator is running at full capacity, and that this line is saturated. So qualitatively, we obtain the same constraints, but if I compute the flows, they are a bit different. We still find that the marginal prices are not very different. Now, the marginal prices ignore losses, so they are here exactly equal to the marginal cost of operation, which was not the case before. Similarly, if I do the second problem we had before, so essentially the problem is now when the lines are not limiting, so I have very high capacity lines, then the only constraints are the constraints of the power generations. Then we find that the optimal power will be here at this cheaper generator. We run it at the maximum power. We still find that the power flows are indirect. So here, the capacity of this line is infinite, practically. But the power, those 400 megawatt, don't go directly from bus 2 to bus 3. Right? This is the difference between a flow routing problem. If I had a graph theoretic problem, well, the problem, if I would be able in electrical grids to route the power. Some people have proposed to make power routers. And we have power routers when we have converters. If we have direct current lines that are transformed. So if this would be DC and we want to have the flow going here, so true DC, not DC approximation of the EC problem, then we could have what is called power routers. The power routers are essentially converting one flow and through power electronic are computing exactly a power injection in the line. If we would do this, then I would send the 400 megawatts that is generated here directly on this line. There's no reason. You have minus 25. That means part of it goes through bus 1. Why is the DC approximation doing this? Well, it is because it is still constrained by those voltage equations here. So this voltage equation that says that the power that flows on the line is constrained to be proportional to the difference of angles. It cannot be set arbitrarily. Well, this is our first class of approximations, the DC approximation. As I mentioned, it's used a lot as a first approximation to solve hard problem. A hard problem that transmission grid operators have is the unit commitment problem. So the unit commitment problem is a problem where we add to the power flow problem a discrete element, as I mentioned an hour ago, which have incorporated the startup or the shutdown costs of generators. So if I'm doing this over now 24 periods of time, for example, over a full day, and one period of time is 1 hour, and if I assume I have ramp-up constraints on the generators plus startup or shutdown costs, then I will have a problem of this kind. It's the same as before, plus there are binary variables, Wi, that are 1 or 0, and that are 1 if and only if the power generation is positive. Now these problems, I can make everything linear except the binary variables here. If I do this, I have what is called mixed integer and linear program. Linear because with the DC approximation I've made everything linear. Now I have those binary variables that make it a mixed integer linear program. So a mixed integer linear program is not a good program. It's a program that you can solve with MILP heuristics, but if your problem is large, that may take days of computing time. So you may need to do something special about it. Right? But this is done with very large computing power. So the grid operators have special clusters to solve those kinds of mixed integer program. And they'll do it with a DC approximation. As I mentioned, the DC approximation will give you the first cut at your solution, and you will need to refine it with a load flow. Quick recap on the DC approximation. And of course, the correct answer is D. The line resistance are ignored, and the voltage magnitudes are set to 1, which follows from the line resistance being equal to 0. One more. So you have to vote again. I'm lazy, so I reuse the same poll. Okay, I close the poll. Ah, it's getting worse. Try again. Usually when I ask to try again, it gets better. By the virtue of truth being, if you try harder, the only thing that resists all arguments are the truth. Right? Didn't work with Donald Trump, but with scientific truth, there is a educational theory that says it should be true. But it's not working now. Okay, I close the poll. And it worked, last minute, right? So the correct answer is D. Of course, A and B are true. Branch power flows have equal magnitude in both directions because there's no loss. So A follows from B. And we have seen that this is true. Now the question is, why is it called the DC approximation? Well, it seems natural because that's as if the AC grid would be an AC grid, which is correct, but not really for power flows, right? This, the DC approximation, the power is equal to this relative to the angle. Now, what it's the same as the DC circuit equations for current versus voltage. So if we're interested in the currents, not the power flows, but the currents, then we have exactly the same maths, the same problem formulation as the DC approximation of AC grids. But if we look at the power in an AC grid, it will still be quadratic somewhere. It will not be a linear thing. But of course, if we know the currents in a DC grid, we know also we can derive the currents from that. We will know everything, the current and the voltages, and then we can get in a second phase the power. But it's not exactly like if we would have a DC grid. Right? So that's the first technique we have seen. It works well for, and it's used for transmission, works well. Well, it is used as a first approximation in transmission grids. And as I said, it needs to be refined typically by separately computing the power losses. In distribution networks, people very often use another technique, which is not very intelligent. It is called local linearization. Local linearization consists in saying if I have a nonlinear thing, like for example the load flow equations in rectangular coordinates, I can approximate them by the first order approximation based on the derivative. Since we have multiple variables, we call it the Jacobian matrix, or the matrix of the differential. Those are synonym terms. So if I call F the mapping that maps the V, the electrical state, to S, the injected power, is given by this equation. Those are the fundamental equations of the admittance matrix, which are true also if there are shunt elements. So in the general case, the shunt elements appear in the diagonal terms. And this is nonlinear. It's quadratic, in fact. If we take the rectangular coordinates, there will be quadratic components in the V's. But I can do a linear approximation by taking if I am at an operating point, V hat, I can take the matrix of all derivatives. So I write this in rectangular coordinates. So for every S, I have 2 coordinates. If I'm in 3-phase, I have 6 coordinates. So I write all the coordinates. And for every formula of the coordinates, I take the derivative with respect to all the V's, rectangular and imaginary parts of all the V's. I obtain the matrix of all derivatives here. And the definition of a derivative is that it is satisfying this. S minus S hat is this. So this is a big matrix. This is a vector. And the missing terms are of order less than this, V minus V here. So this is what we can do now. If we do it in explicit form, the matrix we need to compute is here. I put the rectangular coordinates by putting first the P's and all the Q's. So that means the first line is the derivative of P1, the first coordinate, with respect to all the variables. Now the variables are, here I'm using rectangular coordinate for power and polar coordinates for the electrical state, V and theta, which are the things that work best for this approximation. Then this is the matrix that I'm interested in. This is the matrix of the derivative. And this is a linear relationship. Now, of course, this is only approximate. And second, the linear relationship I obtain depends on a specific point at which I'm doing the approximation. So I need a guess of where the grid is operating. So this is typically done. We'll see that in the lab when you do, for example, quality of service control in a distribution grid, where the grid is operating at a certain level. We measure all the power injections, and we want to curtail some PVs, for example, because there is a voltage problem due to high PVs. So we want to do a small delta from an operating point. So this would be the operating point where we are, and we want to compute the optimal PV curtailment. Optimal here means we want to curtail as little as possible to bring the voltage back into the nominal values. This is a simple case. We can use that iteratively, where this has a name. The idea is very simple. If I want to solve an optimization problem, what I can do is find an initial guess, linearize all the power flow constraints around this value using the Jacobian matrix we've said before. Once I have done this, I'm writing that in a very compact form. Once I have written this, I have linear constraints here. So I have to minimize a cost function, which hopefully is convex, over linear constraints. So I have a convex problem to solve. But this is an approximate formulation. Once I have solved it, I will find an operational point, a solution, which I call S with apex K. And then the idea of this iterative method is once I have found an optimal solution of my approximate problem, I re-approximate the problem around the optimal solution that I had found before. So that gives a loop. Solve this optimal problem obtained by linearizing around the previous point, and you iterate. Now you cross the fingers and you hope that this will converge, that the thing will work well. In practice, for the distribution networks and the kind of OPF problems that we do, people have found that it works, at least it's used routinely. And this has a name, it's called sequential linear programming. Sometimes this is associated with a terminology called the voltage sensitivity coefficient. The voltage sensitivity coefficients are how much a voltage is influenced by power injections. The problem I mentioned before, which is a very frequent problem in grids that have a lot of solar panels, is that the grids have been made and conceived and designed without assuming that there will be lots of solar panel injections. When there is a lot of injections, if the transformer is not able to follow very fast, then there will be overvoltage that might cause some systems to trip. And to prevent it, we would like to curtail the power injections, or better than curtailing, if you have a battery in your grid, you might increase the load absorption by asking your battery to consume that power which comes from the solar PVs. By how much should you instruct the battery to absorb? Well, if you can know what is called the voltage sensitivity coefficient, that says the delta V over delta P. What is the impact of a change in power injection on V, right? Those numbers are called the sensitivity coefficients, and they are exactly equal to the inverse relationship we had before. So a minute ago we said I approximate S minus S hat by a big matrix times V minus V hat. If this matrix is invertible, this is the same as V minus V hat is approximately equal to S minus S hat multiplied on the left by the inverse of this matrix. So the sensitivity coefficients are simply the inverse of the Jacobian matrix. But the bad news is to find, very often we're interested in one sensitivity coefficient. There's one bus where the voltage is too high, and there's one bus where I have a battery, I can do something. So I'm interested in only those sensitivity coefficients. But to find them, we need to inverse the whole matrix, as you know, from calculus. Voila, we do another break, and we resume at 11:15. Now we will see the only non-trivial part of optimization, which is duality. Right. Duality appears naturally in the concept of locational marginal prices that we have seen on the previous example. They are present everywhere in electricity markets, in economy in general. They are used to define what we call supply curves that we will see in the next module when we study demand response. And what we will see now is how they are derived from, for example, the Lagrange multipliers. So as I mentioned already, I'm using as reference formalism for optimization the book of Stephen Boyd and Vandenberg, which has the good property of being available online legally and free. Plus, it's probably the best book today on duality. So I'll give you two slides, which I would call everything you need to know about duality. Of course, they are a bit dense, because So the first thing here, I'm simply copying verbatim what is the definitions in Boyd and Vandenberg. This is the formulation that they use of a general formulation of a convex problem. As I mentioned, there are multiple ways of formulating it, and different textbooks use different formulations, and that's why it's so complicated. But I think it's simple to use only this formulation. So we always cast the problem as minimizing f, therefore f is a convex function, subject to constraints that must be making the thing convex. The constraints can be equality or inequality here, and they are treated differently. Then the first magic tool is the Lagrangian, which is a function of the optimization variable, and Lagrange multipliers that are to be treated differently depending on whether they are associated with inequalities, the lambdas, or associated with equalities, the nu. And the Lagrangian is the linear combination of the objective function, of the inequality constraints multiplied by lambda, and equality constraint multiplied by nu. Now, the first thing is that if the lambda is associated with an inequality constraint, it must be non-negative. Everything is subtle here. If you change the inequality constraint in the reverse direction, and you keep a plus sign here, that means you keep f the same way, but you change the sign, then the lambda would become negative. So all of those things depend very strongly on which formalism you use. So I adhere strictly to this formalism. The dual function is a function of the Lagrange multipliers only, and is the optimal value of an optimization problem where we have replaced the constraints by those linear combinations. So that's the problem that I call L of lambda nu, which is minimize this over now the x. So there can be some constraints in x. Well, I don't say what they are. In general, I keep the same x everywhere. So I put the constraints in x here, and I say overall x here, I remove those explicit constraints that are put here, and I obtain a problem. For every value of lambda and nu, I have obtained a problem. And so that's the main trick of duality. We have replaced a problem with constraints by a problem without constraint. Now, a problem without constraint is easier to solve because, for example, we know if the problem is convex, all we need is to find a local minimum. A local minimum can be obtained by setting the differential, the Jacobian matrix equal to 0, and this will give us, sorry, not the Jacobian matrix, the gradient of this objective function equal to 0. Then it can be a min or a max, but by inspection usually we can find whether it's truly a minimum. So that has a hope of being solvable. If we solve it for every lambda and nu, we obtain an optimal function that depends on lambda and nu and is called the dual function. The second thing to observe is the domain of definition of the dual function. So the dual function is defined for lambda non-negative, as I mentioned, for any nu, but there is an additional constraint. The additional constraint is that this minimum function has a finite solution, which means that this thing should be bounded from below. So the inf of this should not be minus infinity. Right. If we put this constraint, we obtain the domain of definition of this L function, of the problem that gives us for the optimal the G function. And the dual problem consists in maximizing G over all the Lagrange multiplier lambda and nu that belongs to this domain of definition. So each of the problems comes with a domain of definition, capital X for the original problem, which is called the primal, and gamma for the dual problem. Okay. So far it's only definition of what is the primal and the dual, and now everything you need to know about them. I had to reduce the font to make it fit in one slide. The first problem is called weak duality. So P star is the optimal value of the original problem, so the mean of the original constraint problem. D star is the optimal value, the max of the dual problem. And it's always true that D star is upper bounded by P star, which in itself is not always very interesting, but there are cases where we can make use of this. This is true also if we allow infinite values. For example, if the function f, the function is allowed to be equal to plus infinity in this setting, it will be plus infinity that's a way to give constraints in the objective instead of the constraint. If I want, for example, the voltage to be less than something, I can say the objective function is plus infinity when the voltage is above some value. Right. So I can allow this in this framework, and this is true even in such cases the optimal P may be infinite, but this is true in both cases. So that is typically used, for example, to say that if we find that D is infinite, so if the dual problem has an infinite optimal value, that means that the optimal value of the primal is infinite, which intuitively means there was no feasible solution. Well, the best you can do is to find a solution where the objective value is infinite. So this is sometimes used to prove that if one problem is infeasible, for example. But in practice, for us, for solving OPF, it's often not usable. The useful thing is when the problem is convex and is strong duality. Strong duality means the two optimal values are the same, and when strong duality holds, there are a lot more properties that hold, which are given here. So first, when does strong duality hold in this setting? It's complicated to know how in general, but in practice, it's very often we use only this criterion, which is first, the problem is convex, and a mild condition holds, which is called constraint qualifications. Constraint qualifications are true if, remember in the problem formulation, there are equality and inequality constraints. So the equality constraints are typically linear plus constant. That means they are affine, because to make the set, the feasible set constraint in practice, you need the equalities to be linear. So if the equality constraints are linear, and then we need a mild condition that the inequality constraints are either linear themselves or affine, that means linear plus constant terms, and that's enough. If we have this, that's enough. Or if they're not linear, they must be satisfied strictly by at least one feasible point. That means that the set of constraints there must be at least one point that satisfies all the inequalities strictly. The inequalities are less than or equal. So there must be a feasible x. There must be a point x that satisfies that strictly. Maybe hard sometimes to verify, but sometimes not. But if we have inequality constraints, then this is true. So in practice, for most problems, this is not a difficulty to show those arguments, those criterion, which are called constraint qualification. If this holds, then we have a boulevard of nice things that follow. All those things follow. If x star is an optimal of the original problem, that's what we're looking for. If lambda star nu star is an optimal of the dual problem, then we have that, then the value of the problem for those two are equal. Those are the optimal values. Second, x star is an optimal solution of the problem without constraints, where we have taken the values of the Lagrange multipliers exact to the optimal value. Remember that the L is the problem where we replace the inequality and equality constraints by a change of the objective function, lambda times the constraint and nu plus nu times the constraint. So if an oracle tells you that's the value of lambda star nu star, the optimal value, then you can solve this unconstrained problem and you will find exactly the x star. This has also an important interpretation. That means that we can interpret the lambda star and nu star as marginal costs, because we're saying instead of having the hard constraints as they are, we have you pay a penalty. Here we say we should have fi negative, but instead of that we say if the value of fi is positive, you pay a penalty lambda I. Right? And then it's saying that if you replace the hard constraints by those penalties for violating the constraints, and if the values of the prices are exactly the optimal multipliers, then it gives exactly the same value, which is interpreted in the converse direction by saying we can interpret those value lambda star as the price we would need to pay to violate the constraints. Then a third property is called complementary slackness, which means that at the optimal, if a constraint, an inequality constraint, is satisfied strictly, then the corresponding marginal price or Lagrange multiplier is 0, which means this constraint does not really play a role at the optimal. If it's strictly negative at the optimal, because all those functions are assumed to be at least continuous, then it will continue to be strictly negative around the optimal, and then we can ignore the constraints in the neighborhood of the optimal. The KKT condition, Kuhn-Tucker, I believe there's also Karush, to whom this is attributed. It's also called sometimes the principles of dependent extrema. It says that at the optimal, we must have this stationarity condition. This is simply saying that we're trying to find the optimum of this. So I take the gradient with respect to x. Right? So the gradient with respect to x is this, the gradient of the objective function, plus something that involves the gradients of the constraint. And we're saying that at the optimal, this must be true. Well, this follows directly from this, because we know the optimal is an optimal of this problem without constraints. But the interesting thing is in the reverse direction. This is necessary and sufficient if you find some x star, lambda star that satisfy this equation, and we have complementary slackness, then they will give you the optimal. So this is very often used to find numerically the optimal, at least for the good problems where we can do things analytically. So those are the first two results. Then there is a third one, which is independent of whether the problem is convex or not, which is called a saddle point. Saddle point is if you find a point x star that is optimal for this problem, lambda. So I still don't know whether lambda star and mu star are optimal, but I solved equations by putting as condition that x star must be optimal for this problem, which again is a non-constrained problem, so easier to express analytically. I need, in addition, to have the complementary slackness. Then, to see whether I really have a solution of my original problem, the only thing I need to do is to check whether the x star is feasible for the original problem. So the first result here was saying, if an oracle gives me lambda star and me mu star, the only thing I need to do is to solve this problem. Here we're saying something different. I will look. I don't have an oracle because oracles don't exist, as you know. Nobody knows the things that we don't know. So I will look for lambda and mu by solving this problem. For every lambda and mu, I will solve for x. The x I will obtain depends on lambda and mu. And then I will look for lambda and mu such that the x that I have found satisfies the constraints of the original problem. That's a technique that's very often used. If we have found such a point, such an x, that for some lambda and mu is optimal for the unconstrained problem and in addition satisfies the original constraint, we have obtained what is called a saddle point of the problem. X lambda nu is called a saddle point of the problem. And a saddle point has the property that the x is optimal for the original problem and lambda nu is optimal for the dual problem. So if your problem is convex and satisfies constraints qualifications, it's a good strategy to look for saddle point. You know there is a saddle point, the optimal solution, and you know that strong duality holds. But the other way around is true also. If you have a problem for which you happen to find a saddle point, then strong duality must hold, even if the problem is not convex. Though in practice, finding such problems which are not convex might be an issue. So what I mentioned a minute ago is if we the interpretation of the Lagrange multipliers as marginal costs are given here. If I consider a problem put in this form, and I now consider that the constraints that are given here, they can be varied. So those constraints are typically, for example, the capacity of a generator, UI. So if I increase the capacity of the generator, what happens to my problem? So I call C the optimal cost of my problem. And then the theorem says that if the problem, if strong duality holds, and if everything is differentiable, then the derivative of the optimal cost is exactly minus the optimal Lagrange multiplier. Minus, because here we're talking of cost. If I interpret minus the cost as the value that I get from my system, then I see that the derivative of the value would be plus the Lagrange multiplier. So this is interpreted as the shadow price of the constraint. It is saying that adding a small epsilon to the ith constraint, so typically more capacity, will decrease the cost by lambda I epsilon, or would increase the value by lambda I epsilon. So I could trade, I'm willing to buy more capacity if the cost of buying this more capacity is less than lambda I. If it's more than lambda I, then I don't benefit from this. Let's test this on a small example. So, we have seen a small optimization problem, which is the problem on slide 15, right? So on slide 15, we had max Why does it not work? Okay, I'll write it on the board. On slide 15, we had a small linear problem, and what I'm asking you to do now is to write the dual. We had max x plus y over the constraints x plus 2y less than 10 2x plus y less than 8 That's my problem P. So the question is, can you formulate D? It's an important step. We'll do it in the lab, for example, because we will see that when we do robust linear programmings, we constantly have to formulate the dual of the problem, of subpart of the problem. I propose to do it on the board now. Is that okay? Well, the first thing I will do is first transform it into a problem that is in the exactly as written in my catalog of problems. I want to have only one way of formulating the problem, so I have to minimize something subject to negative inequality constraints and equality constraints. So transform everything to make them the correct way. So instead of maximizing x plus y, I will minimize minus x minus y. Of course, I will need to remember that the optimal value of this one is minus the optimal value of this one. So the problems are not exactly the same, but the mapping from one to the other is trivial. Subject to the constraint, well, I can take all those constraints as negative things by saying x plus 2y minus 10 is less than 0, 2x plus y minus 8 less than 0, minus x less than 0, minus y less than 0. I can do this, that's trivial. But now I have a form that is exactly according to the book. I minimize a function, which is convex, it's linear, subject to inequality constraints that are affine, and equality, I have no equality constraint here. So I need to introduce the Lagrange multipliers. I have the lambda and the nu. The lambda corresponds to the inequality constraint. The nu corresponds to the equality constraint. I have no nu, I have only lambda. And I have 4 of them. So I have 4 multipliers. So my Lagrangian is L of x, y, lambda 1, lambda 2, lambda 3, lambda 4, and is equal to the objective function, which is minus x minus y, plus lambda 1, the first inequality, plus lambda 2, the second inequality, I can go outside the slide now, it's beautiful, plus lambda 3, the third, plus lambda 4 minus 1. That is my Lagrangian. And the constraints are on lambda 1. All the lambda I must be non-negative. That's the theory that says the multipliers associated with inequalities must be non-negative, right? That's the Lagrangian. Now I need to formulate the dual problem. So I need to find the domain of definition of the dual problem, which is the set of value of lambda such that this is bounded from below. So when I will take the optimal value over x and y, I need to find values of lambdas such that this is bounded from below. And this is the trick. When is that bounded from below? Well, this is now, I optimize this over x and y. That's a linear function of x and y. A linear function of x and y, in general, is not bounded from below. Right? If I take, for example, if I forget this, if I take minus x minus y, I ask you, what's the minimum of this over x and y? Well, the answer is minus infinity. You can always have values of x and y, such that this is as large in module and negative as you want. So this is not bounded from below. What are the linear functions that are bounded from below? Those are the ones that are constant. If there is a non-zero coefficient in front of a variable, you can always compute values of the variables that will make this as large, positive, or as large in absolute value and negative as you want. So this is bounded from below, or from above, by the way, which means the dual problem has a finite, doesn't give minus infinity, if and only if the coefficients of x and y are 0. That's the trick. The rest follows from this trick. Now, what is the coefficient of x? Coefficient of x is minus 1 plus lambda 1 plus 2 lambda 2 minus lambda 3. That's the coefficient of x. If I print this as it's a big linear function of x and y, I put all the x together, I will have this as a coefficient of x. In other words, L of x, y, lambda 1, lambda 4 is equal to this times x. Coefficient of y is minus 1 plus 2 lambda 1 plus lambda 2 minus lambda 4, y. And then the rest is minus 10 lambda 1 minus 8 lambda 2. That's my Lagrangian. And this is bounded from below, requires that this must be equal to 0. And this must be equal to 0. All right. That's my condition for this dual problem to be well defined. That means the domain of definition in lambda of the dual problem is given by those two constraints. Now let's continue. That means the domain of definition of the dual problem is defined by the constraints lambda 1 plus lambda 2 plus 2 lambda 2 minus lambda 3 equal 1, and 2 lambda 1 plus lambda 2 minus lambda 4 equal 1, and we also have the condition that all the lambda must be non-negative. That's the domain of definition of the dual function. Now, what is a dual function? G of lambda 1, lambda 2, lambda 3, lambda 4. It is the minimum of the Lagrangian over all value of x and y, unconstrained. Right? So it's the inf over x and y of the Lagrangian. The Lagrangian is the equation here that I write with a star. So definition, I'm just applying the textbook definition. The G is the solution of the dual of the intermediate optimization problem where I've removed the constraint and replaced them by the Lagrangian in the objective function. Now, if I am in this set, the Lagrangian is simply the coefficients disappear. There's only the constant term minus 10 lambda 1 minus 8 lambda 2. That's an optimization problem over x and y. Lambda 1, lambda 2 are fixed. So this is minus 10 lambda 1 minus 8 lambda 2. That's the dual function. So the dual problem is minimizing the dual problem, the dual function, over the set gamma. So the dual problem, D, which I call prime because that's the current that corresponds to P prime, is maximize the dual function minus 10 lambda 1 minus 8 lambda 2 subject to the constraint lambda 1 plus 2 lambda 2 minus lambda 3 equal 1, 2 lambda 1 plus lambda 2 minus lambda 4 equal 1, and all the lambda non-negative. That's the dual problem, right? Now, if I want the dual problem of my original problem, which was not P prime but P, I need to take the minus the objective function of this. So minus the max of minus thing is the mean. So D is min 10 lambda 1 plus 8 lambda 2 subject to the constraint, about the same constraints here. Subject to the constraints, which are the same that I will rewrite. So it's completely mechanical, so we can hope one day machine learning stuff will do it for us. But in the meantime, it's good to know how to do it. So if I compare the original problem and the dual, we find that the original was a max of a linear function with linear constraint. The dual is a min over the lambdas now with also linear constraints. And we find that the coefficients here, 10 and 8, the coefficients that appeared in the inequality constraints, appear as coefficients of the objective functions. And vice versa, the coefficients of x and y in the original problem appear as the right-hand side in the constraints. And so there are very mechanical things you could derive exactly by having rules, but perhaps the simpler is to redo the thing we did every time. We will use that next week when we will have problems where we want to change a max into a min. So that's the main value of duality of linear problems. When we have a problem with max, and for some reason we would like to transform it into a problem of min, then we can. That's the beauty and the magic of duality. Voilà. In the slides, there is more. There is something that I call test your Lagrange duality. So I would like to ask you to do that at home, and I will post the solutions on Friday. If you feel very comfortable with that, you can skip it, if this is all bread and butter for you. Otherwise, if you're not comfortable, I'm asking you to study this small optimization problem, which is now a bit more complicated. It has quadratic constraints, but this is a convex set. X2 plus Y2 less than C, that's the disk, centered in 0 with radius square root of C. And I want to minimize a linear function over the disk. Right? So that's fairly simple to know. You're in a disk. You want to find the optimal of a linear function. It is somewhere at the edge of the disk, where probably the normal will be a normal to this. So it's not a problem where duality helps to solve. We can solve it exactly. But I ask you to use all the different elements of duality and see what it gives to this problem. You will see that they all give different viewpoints on the same problem. They all give the same solution, but they give different, sometimes complementary approaches, redundant. I mean, if you solve it with one method, you don't need to apply the other methods, but you can solve it with different ways. You can solve it using the Karush-Kumtaker conditions. That will give you an optimal. You can write the dual problem and solve the dual, which is a radically different problem. And this one will be easier. It will be unconstrained, so you will be able to solve it. Or you can look for a saddle point, which is yet a different approach, and see how they work. Once you have done that, then we're able to understand the locational marginal prices. If we have a formulation of the OPF that for which Lagrange duality holds, then we will have, so particularly if we put it in this form, then if f is the cost, then the locational marginal price is the derivative of the cost with respect to the load, active power demand at a given node, for example, at node 1. Then we know that the derivative of the cost with respect to each of the constraints, ui and vi, is given by the Lagrange multiplier. Now, if the constraints are themselves expressed as a function of L1, which in our case are linear functions, then we have, obviously, this function. The derivative of C with respect to L1 is, by the total derivative formula, is the sum of the chain derivatives here. I did this for this example, which is the DC formulation of this example. This is a problem we've seen an hour ago. So we have those simple expressions with the angle theta, and I have the constraints on the power flows here. I have 16 inequality constraints, so I have 16 Lagrange multipliers. I have 16 because they multiply because of the absolute values. 1 minute and we're done. So the Lagrange multiplier here are they're called nu here. I find, for example, that the inequality constraint with respect to the first equality, so equality 1, this one here, the three equalities, 3 Lagrange multipliers, 16 equalities, 16 Lagrange multipliers. And the L1 appears only, for example, in the first inequality. So here it's very simple. The marginal cost is equal to dc over dl1, which is minus the Lagrange multiplier, multiplied by the derivative of this with respect to L1, which gives another minus sign, so it's exactly equal to this Lagrange multiplier. And similarly, if you look at the two, so this is how we find, for example, the marginal prices here. If we look at the inequality constraints, we find here the 16 Lagrange multipliers, and what do you observe? They're practically all zeros, except 2. What does that mean? Remember the complementary slackness. If the Lagrange multipliers for inequality constraints are non-zero, that means that this equality is binding. And if they are 0, the inequality is not binding. That means at the optimal solution, the inequality is strict. All inequalities are strict, except those two, which is for P2, 3, and for G1 max. So that also gives us the information. That means what are the bottlenecks in this system? The bottlenecks are the capacity of the line 2, 3, and the capacity of the generator 1. All the others are not limiting at this operating point. Voilà, that's the end for today. There are a few slides that we haven't seen with polls and questions, but I will post the solutions towards the end of the week. Thank you.